Okay, so in this video, we will consider our first example of finding the volume of a non-trivial solid of revolution. Now to generate a solid of revolution, we need two things. We need a region in the xy plane and an axis of revolution. So consider now the following region. So look at the curve y equals root of x. This will be one boundary of the region. The other boundary will be the y-axis. And the third and final boundary will be given by the horizontal line y equals 2. And of course, if y is 2, x must be 4, as the square root of 4 is 2. So we now have a clearly well-defined region in the first quadrant of the xy plane, bounded by the curves y equals root of x, the y-axis, or if you prefer, x equals 0, and the horizontal line y equals 2. And we will take quite simply the y-axis as our axis of revolution. Now you can imagine revolving this region about the y-axis. It will generate a very interesting solid that you can visualize, and let's try and reproduce here a three-dimensional picture of this solid. Again, obtained by revolving the region about the y-axis. So again, you can see the center of your solid will be the axis of revolution. So you can imagine again the axis of revolution passing through the center of your solid, and you can see within your solid the given region, right? So you see it right here. This is the region in the xy plane, and as you revolve this region a full 360 degrees about the y-axis, you generate this very interesting solid. And the question we're asking, of course, is what is the volume of this solid? Well, as always, we have to make a choice. Do we take a vertical slice of our region or a horizontal slice? Here, we will take a horizontal slice. So consider a horizontal rectangle. The position is along the y-axis, and so you can ask, well, okay, if we have now a rectangle that is 1 perpendicular to the y-axis, 2 always touching the y-axis, what is the solid obtained by revolving this rectangle about the y-axis? The answer is, of course, a disk. And you can picture this disk within the full complex solid revolution, right? This will be a cross-section of the full solid, so you can imagine looking something like this. So if you can imagine slicing through the full solid two places, if you slice through it in both of these places, you'll obtain a small disk. Well, what is the volume of this disk? We know we have to find the radius and the thickness of our disk. Well, the thickness is quite easy. It is the width of our rectangle. The width is an infinitesimal change along the y-axis, so of course it is given by dy. Now the radius is the length of the rectangle. If you look, the length of the rectangle is a horizontal segment, so a segment along the x-axis. So we need the larger x value here and the smaller x value here. So if you draw down the two endpoints of the rectangle across the x-axis, well, clearly the left-hand point, the smaller x value, is x equals 0. Now what about the x value of the right-hand point of the rectangle? Well, at the right-hand point, we are on the curve y equals root of x. Now we want, as this is dy, everything we measure must be a function of y, and here we want the x value given y. Well, on the curve y is the root of x, as we are in the first quadrant, everything is positive. So if you square both sides, of course, you'll get that y squared is equal to x. So the x value at this point as a function of y is simply y squared. And now the radius can be easily obtained. Right? The radius, once again, is the length of the rectangle. It is a line segment along the x-axis, so to find the length of this segment, we take the bigger x value, y squared, minus the smaller x value. Here it happens to be 0. So we are left with simply a radius of y squared. Now be careful that in some problems, the smaller x value may not be 0. So always be careful that when you have a horizontal segment and you want the length, find your two x values, the larger one and the smaller one, and by subtracting the larger minus the smaller x value, you have the length of your rectangle. And now we're good to go. So the volume of this little cross section of the full solid of revolution, being this disk, is given by, we know, the surface area, so pi r squared, as the region is a circle, times the thickness of our disk, dy. But as the radius is y squared, if you square the radius, you get y squared squared, which is y to the 4. And now we have the volume of our little disk, right? This little cross section of the full solid has a volume of pi y to the 4 dy. And now the question is, of course, how do we, from knowing the volume of a little slice, a cross section of the full solid, how do we get from this the total volume of the solid? Well, hopefully you can answer this question, but there it is. So you say, well, to find the volume of the total solid, we will find the volume of a little slice of it, a cross section, given by pi y to the 4 dy. And to find the total volume of the solid, we have to add the volume of all of the little cross sections. So adding, of course, is summing, is the action of taking the integral. So we must sum the volume of all of these little disks over the entire solid. And if you look, the disks are generated by revolving the rectangles. And the rectangles begin along the y-axis, because again we have a dy, so everything must be a function of y. Now the rectangles again generate the disk. We must sum the volume of these little disks, the cross sections of the full solid, and the cross sections or the rectangles begin when y equals 0, and they end all the way up to y equals 2. And this will give us the total volume of our solid. As we add, given every little rectangle from 0 to 2 along the y-axis, the volume of every little cross section, we will in the end obtain the total volume of our solid. And now we can find this integral using, of course, the fundamental theorem of calculus. And this integral is essentially trivial. Pi stays there as a constant multiple. Y to the 4, we use the power rule, y to the 5 over 5. This is our antiderivative of pi y to the 4, and we must evaluate from 0 to 2. So at 2 to the 5 is 32 over 5 times pi, so it's 32 over 5 times pi, minus the antiderivative when y equals 0, but if you replace y by 0, you get nothing. So this is the total volume of this really nice solid of revolution. And that's it. In our next video, we will consider this exact same problem. So we will look at the same region, the same axis of revolution, and we're going to ask, let's find the volume of the solid, but now instead of using a horizontal rectangle, we will use instead a vertical rectangle. Hopefully, even though we have a different, and you'll see in the next video, a different little solid, we will obtain the same volume.